Okay, so a confidence interval is very similar to what we saw with margin of error. And we'll actually use some of those same terms again as we're working with them. But what's important to recognize is that this is our first test of statistical significance. Okay? And we'll look at what that means. Today we are concentrating on population means for our confidence intervals. We're going to be using this same procedure for other measures like proportions, difference of two proportions, difference of two means. So we'll explore these in the subsequent weeks, but once we understand this procedure, procedurally they're all the same, and that's good news. And we'll see the same kind of thing with our inference testing as well. Now, I've been saying this for a long time. Okay? The purpose of statistics really is to use our sample to say something about the population. So, we spent a lot of time in the beginning of the year trying to make sure that we took a sample that was large enough and representative of that population that it's describing. Okay? But we don't know these population values necessarily. Nor do we, now don't misinterpret what I'm saying, nor do we directly care about what our sample does. We care more about how well our sample represents that population. Okay? There's some variability. Okay? The reason for taking a sample is to infer from that data some conclusion about the wider population represented by the sample. And that's what statistical inference does. It provides methods for drawing conclusions about a population from sample data. Now, just like we saw with our probability distributions, binomial, geometric, and so forth, we have rules that we need to follow and conditions that need to be met in order to use these rules. Now, look at what we have for this, okay? We start with conditions that seem straightforward, but when you start to think about actually satisfying the conditions, it's impossible, right? First one, we have a simple random sample from the population of interest. There is no non-response or other practical difficulty. The population is large compared to the size of the sample. All right, well, we talked about all the issues with a simple random sample, okay? How we need that population frame that's not always practical. We looked at a bunch of different methods, okay? Secondly, there is no non-response. Come on, like, you know people like to give you a hard time. They don't want to participate in surveys that you conduct. That's not really practical, or any other practical difficulty. That you get a perfect sample. Everybody who you say should be in your random sample agrees to participate, and they give you nice results where the variable that we measure has an exact normal distribution in that population. Okay? We don't know the population mean, okay, because that's the purpose here. We don't know the population mean. However, we do know the population standard deviation. Like, where does that happen? Where, yeah, I don't know what the average is, so I'm going to set up this confidence interval to find what that true population mean is, but I do just so happen to have the population standard deviation. No. Okay, these conditions, they're unrealistic, every single one of them. So, with that being said, the best we can do is to give a little bit of a margin of error and give a little bit of buffer and say, well, I can use probability models to describe how certain I am that I'm pretty close to that true population parameter. Okay? That's essentially what's happening here. So we have an example that we're going to kind of work through this process with together. says a National Health and Nutrition Examination Survey, or the acronym NAMES. This report gives data for 654 women aged 20 to 29 years and looking at their BMI, body mass index. I always want to say BAS. The mean BMI of these 654 women was 26.8. So here is our sample mean. On the basis of this sample, we want to estimate the mean BMI for the whole population of 20.6 million women who fit in this age grouping in the country. So to match these simple conditions that we just looked at on the last slide, we will treat this NAMES sample, pretend it's a simple random sample from a normal population, and the standard deviation, they give us a number here. I'm going to talk more about standard deviation at the end of class, okay? But let's just play into their little fantasy here that we don't know the population's mean, but we do have the population standard deviation of 7.5. Yeah? Now, to estimate the unknown population mean BMI, we have X bar 26.8. We don't expect X bar to be exactly equal to mu, the population's mean. So we want to say how accurate this estimate is. So what we could do is look at a sampling distribution. We just spent last week talking about our sampling distribution where that population's mean can go right there at the center, and the standard deviation step size for that distribution is found by doing sigma divided by the square root of n. So in this case, that standard deviation we see right here, 7.5 divided by the square root of 654, gives us about 0.3 as our standard deviation step size on the sampling distribution. So we had, 26.8 right there, step size of 0.3, 0.3, 0.3, going to the left and going to the right. Now, let's use our empirical rule, 68, 95, 99.7. I will say that most of the time, we are going to concentrate on this 95% part of the empirical rule, and we'll look at that further in a few minutes. But that would mean 2 of these standard deviations of 0.3, 2 to the left and to the right. So we're looking at here to here. And we want our interval to cover this ground from our sampling distribution. So let's put that into play here. We had 26.8 as our X bar. We're going to subtract and add 2 of those 0.3s because it's 2 standard deviations below and 2 standard deviations above. So this was like adding and subtracting 0.6. 26.8 minus 6 takes us down to 26.2. Add 0.6 takes us to 27.4. So that's a 95% confidence interval. From the empirical rule, we said 95% of our data is between those 2 values. Essentially what's happening, we are 95% sure that that true population mean is going to be between these 2 numbers. Our sample mean was 26.8. Maybe the 20 million people who are in this category, maybe they actually do have a mean of 26.8. But there's some natural variation. We would expect that that population's mean is going to be pretty close to that, but at least between 26.2 and 27.4. So basically what's happened here is what we talked about with margin of error, way back with proportions in the first semester. We have our estimate. That's kind of like our stem, and then plus or minus the margin of error. Okay? We go a little below and a little bit above. That little bit is based off of our standard deviation calculation for a sampling distribution, sigma over square root of n. Now, with this confidence interval, okay, it says a level C confidence interval for a parameter has two parts. An interval calculated from the data, which has this form that we just talked about, and it gives the probability that the interval will capture the true parameter value. Think about what that means. You're saying that there's a 95% chance, 19 out of 20 times, that population value is going to be in this interval. Now, on the flip side of that, you're acknowledging that 5% of the time, or 1 out of 20, you're going to be wrong. And that actual population value is not on the interval. Okay? This confidence interval, it's the success rate for this model. 95% is pretty good, but it's not perfect. We don't know whether the 95% confidence interval from a particular sample is one of the 95% or one of the unlucky 5%. Okay? To say that we are 95% confident that the unknown mu lies between 26.2 and 27.4 is shorthand for saying we got these numbers using a method that gives correct results 95% of the time. Let me show you a simulation here that helps, I think, demonstrate this a little bit. 1 second while I flip screens. Okay, so this is kind of like a simulator that we had seen last week. Now, we have two normal curves here. The gray one is the population's distribution. The dotted red one is the sampling distribution. And you can see we have a couple bars here. We could play around with these values. We're going to leave it as 95% level of confidence. Our sample size, doesn't really matter for us here. We'll just leave it at the default of 20. Now, what this is going to simulate is taking a sample after a sample after a sample and seeing how that sample's mean relates to the population's mean. Okay? This green line is the center of both of these curves. It's the population's true mean. So let's take one sample. And you can see that our sample's mean, where that black dot is just above the green line. It was pretty close to the population's mean. This gray bar is the confidence interval. So essentially, we're going to take sample after sample and see how many of our samples, how many of their confidence intervals include that green line. Okay? We would expect 95% of them to, or 19 out of 20. So let's take another sample. We're still good. Another sample. We missed. This one, you can see we had a sample where our data is a little bit higher. Okay? We actually have a very small value, but a very big value as well. And it's pulling that mean to the right. And it pulls that confidence interval above where our true population's mean is. But we take another sample, we're good. That's almost perfect. Another sample, we're good. So 4 out of 5, we have had accuracy with our confidence intervals. Let's take 25 samples at once. Okay? We missed on another, and we missed on another. So we've missed 3 of our 30. So we're 90% right now. Take another 25. Okay? We've missed a few more. Okay? But we know, law of large numbers, this is meant for the long run. Okay? You can see, I know it's small, but our percent hit. 89% of our samples have been good. But if we keep taking more and more, we expect this number to get to 95%. 92, 94, yeah, we're pretty good. Now, 218 of our 230 samples have hit the confidence interval. So that's what's going on here. The big picture. If you had nothing better to do and you took sample after sample after sample of the same size, a confidence interval says that in the big picture, 95% of them will hit. But on the small scale, on the individual basis, it's just like probability. We don't know what's going to happen. But there's a 95% chance it's good. Any questions about that so far? Okay. Let's go back. Now, not to confuse you even more, but I will say 99% of the time, you will be using a 95% confidence interval. Okay? Process that for a second. We almost always use a 95% confidence interval. But that's not set in stone. Some other common levels of confidence are 90% and 99%. Looking at this 95%, okay, we had shown that with the empirical rule that it was 2 standard deviations below and 2 standard deviations above. Well, I've kind of been lying to you for the last several months. It's not exactly 2 standard deviations. It's actually 1.96 standard deviations if you were to look at the z-score chart precisely. But that's so close that we often just round that 400ths up to an even 2 for the reason that that's a pretty good level of confidence, and it's doubly nice because it's an easy calculation to do. We just take our sigma over the square root of n, and we multiply it by 2 for our 2 standard deviations above and below. If we wanted a 90% confidence interval, that we could get from our z-score chart. That's 1.645 standard deviations. So instead of multiplying by 2, we have this number down here that we call z star. Z star from the z-score tells us how many standard deviations above. When it's a 95% confidence interval, that's a 2. If it were 90%, that's 1.645. Okay? So what's happening there is that you have fewer standard deviations away. So you're lowering the confidence, but that margin of error, okay, what had been from here to here, I'm 95% confident that my actual mean is from here to here. If I have a smaller standard deviation, now I'm zooming in on that a little bit. Okay? But there's a sacrifice for that. I'm lowering my level of confidence that the true value is actually there. It had been 19 out of 20 times, 95%. Now, the price to pay is I'm only 9 out of 10 times going to have that true value. Go back to the empirical rule. 68, 95, 99.7. If I wanted this Z star value to only be 1, I'm going to have a nice narrow confidence interval. But the price to pay for that is I'm only 68% sure. Now, only 2 out of every 3 are going to be accurate. I can go back to that applet, that simulator that we just showed, change that level of confidence down to 68%. Okay, I'm going to get a lot more misfires there. Okay? But my confidence interval is nice and narrow. Okay? I'm 68% sure that my true value is between 1 and 2, but that's pretty uncertain. On the other end, 99% sounds nice. Okay? Wouldn't it be great to say, I'm 99% confident that the true value is between this and this? But the sacrifice there is that that standard deviation is now more than 2.5 standard deviations away. Think about that on the normal curve. Is it at all helpful to say, okay, there's 1, 2, 3, 1, 2, 3, here's the mu mean. Is it helpful to say that I'm 95% confident that the true value is somewhere in here? Not really. That confidence interval is like there to there. Yeah, I'm 99% confident that it's between here and here. Well, of course it's between there and there. You're not really going out on a limb. So, this 95% confident, it's a nice balance of both level of certainty and practicality in terms of the width of the interval. Okay? You don't want it to be too narrow, okay? Although narrow would be nice. You don't want it too narrow at the sacrifice of level of certainty. But on the flip side, you don't want it really certain, but then that confidence interval is really wide. Okay? It's like what? Goldilocks and the Three Bears, right? Too hot, too cold, just right. 95% confident. All right, we just talked about this. It's kind of saying the same thing about what happens when Z gets smaller, that Z star. Okay? If Z star gets smaller, that means that the confidence is going to diminish. Okay? Yes, the number of standard deviations is going to get smaller, but so is that level of confidence. As sigma gets smaller, sigma is the population standard deviation. Okay? It is easier to pin down when mu and sigma is smaller. Or, I'm sorry, it's easier to pin down what mu actually is when the standard deviation is smaller because you have less variation in that population. The sample size, that's the other thing that you can control. We know the bigger the sample size, the better. When the sample size gets larger, you're more certain that that's truly what's happening in the population as a whole. And you're dividing by a bigger number. So that means that this size of your width, your margin, is going to get smaller. We'll see that in some example problems. All right, so I have a problem that, ignore the messed up X bar right there, but this says we have a simple random sample of 400 high school seniors who gained an average of 12 points on their second attempt at the math portion of the SAT. So they took it one time. They were told that, well, practice helps you with this. If you take it again, on average, students do better. And the average increase across this sample of 400 students was 12 points better. So assume that the change in the score has a normal distribution with a standard deviation of 42. So we have our X bar, we have our sigma. We want to estimate the mean change in score in the population of all high school seniors. So letter A, give a 95% confidence interval for our mu based on this sample. All right, well, we know we're following this equation. X bar plus or minus 2 for a 95% confidence interval of our sigma standard deviations over the square root of A. This is our equation for a 95% confidence interval. So we can substitute our values in 12 plus or minus 2 of these 42 for our standard deviation divided by square root of 400. And, oops. Glad I got that on the recorded version, right? We know that square root of 400 is 20. I'm going to show the work here, but in the future, like, you could just like do this as a single calculation. 42 divided by the 20 gives us 2.1. So we've got 12 plus or minus 2 times 2.1. So there is that, it's called standard error. Okay, we're taking 2 of those below and above. So 12 plus or minus 4.2. Now, a couple things. Kind of nitpicky, but it's common sense. We call this symbol here plus or minus, but you're doing a confidence interval. Do the minus first, and then the plus, right? You want the smaller value and then the larger value. We read left to right. Okay? Nothing kind of bugs me more than when I'm like grading tests on confidence intervals and I see people have the larger answer and then the smaller answer. It shows that you don't really know what's going on. Okay? So let's do the minus first here. 12 minus 4.2 takes us down to 7.8. 12 plus 4.2 takes us to 16.2. And this is how we show a confidence interval. Okay? Kind of like an ordered pair. Okay? Lower boundary, then upper boundary. And we would interpret this as we are 95% confident that the true population mean is between 7.8 and 16.2. But that actual nationwide average improvement when taking the second, or taking the SAT math the second time, the average improvement is between 7.8 and 16.2. Any questions on that? You can see here that the calculations themselves aren't really that bad. We have our equation, get it set up, put the numbers in, follow the order of operations, and solve. Letter B says, based on your confidence interval, how certain are you that the mean change in the score mu in the population of all high school seniors is greater than 0? And they give you a hint. Does the interval from part A include 0? Well, no, it does not include 0. In fact, it's not really anywhere close to 0. And that's a good thing. How certain are we that the mean change is greater than 0? We are very confident. Because this interval is entirely above 0. And it's not just that we're barely above zero. Okay, we saw how we're misfiring with all of our samples. Okay? We're pretty sure that even if we're slightly outside that 95% confidence interval, that it's not going to include zero here or go into the negatives. Questions there? All right, now let's manipulate this a little bit. Okay, same numbers here, but now it wants us to find a 90% confidence interval and compare it to what we just got. So slightly less confident. What do you think is going to happen here? When we're 95% confident, it goes 7.8 to 16.2. If we're decreasing that level of confidence, you can tell me what's going to happen with these boundaries. Is it going to get more narrow, or is it going to get wider? Well, let's see. 90% confidence interval. We have our sample mean, which we said was 12, plus or minus 90%. Now, as I said, we are typically doing 95, so I don't even remember off the top of my head what the 90% Z star is. Okay, I see it right here. It was 1.645. Okay, 1.645. That's replacing the 2 times. Our standard deviation is still the same, 4.2. Sample size still the same, 400. Okay, so we know that this gave us a value of 2.1. Okay, so again, I'm showing you a little more work than we need to show here. But try not to throw the calculator this time. 1.645 times 2.1 gives us a step size of 3.4545, or that margin of error is essentially what that is. 12 minus this, 8.54. 5 to 12 plus 3.4545, 15.4545. I could have done that in my head. Monday morning, you know. Don't trust yourself. So let's compare. We're essentially saying now, with our 90% level of confidence, we're 90% sure, 9 out of 10 times, our population mean is going to be between 8.5 and 15.5. Before, we're 95% sure it was between 7.8 and 16.2. So what we've done, we've narrowed in our intervals a little bit. Okay, we've zoomed in on it. However, the price that we paid is we've lowered our level of confidence. Okay, now only 9 of 10 will be there as opposed to 19 out of 20, 95% confidence. Questions with that? Okay, that's what B was saying. So letter C, let's play with this a little bit more. Suppose we had a simple random sample of just 100 high school seniors now. So now we're going to mess with the sample size. What would be the margin of error for the 95% confidence interval, but only across a sample of 100 people instead of the 400? So we're only taking a quarter of the sample size. Okay. Let's look at what happens. Okay. Still have our 12 right there at the center. We're going back to plus or minus 2 of the sigmas, which were 42, divided by the square root of only 100 this time. Square root of 100 is 10. 42 divided by 10 is 4.2. So 2 of those, we're doing 12 plus or minus 8.4. So our confidence interval for 95% is going to be 12 minus 8, 4.6 to 20.4. Look how wide that is. No, I messed that up. 3.6. 3.6 to 20.4. Okay? And what had been 7.8 to 16.2. Okay? Still that same 95% level of confidence, but with this one, we were looking at that across 400 people. 400 people is a pretty healthy sample size. We're pretty sure that this is actually representing the population as a whole. Now, with only 100 people, if there are extreme values, that's messing up with our data a little bit more. It has more impact. Okay? There's more of a chance that variation is going to have an effect on our data. And look at this, our question before about 0, before when it was 7.8, we didn't really worry about it. But now, I mean, we're still above 0, but 3.6, maybe there's a chance that, that we could get no difference between taking that test the first time and the second time. And it's totally like changing your interpretations or your conclusions. So there are a lot of different things that can contribute to your interpretation. Level of confidence, sample size, consistency of your results with respect to the standard deviation in the population. Okay? All of those things kind of come into play, and it's this balancing act between how certain do you want to be and the width of that interval. Anybody have any questions here? Good. Okay, so what I'd like us to do right now, on Canvas, I have something called confidence interval practice for means. It's 3 problems where I just want us to pull this up and try these 3. Okay, now we're doing a 95% confidence interval on each one of these, so that's fine. I told you that that's what we're usually doing. Man of my word. Our first problem, national average for the number of students per teacher for all U.S. public schools is 15.9. A random sample of 50 Pennsylvania school districts shows that the mean number of students per teacher was 19.2, with a standard deviation of 2.1. Find a 95% confidence interval for the true national average. How does the national average compare? Okay? So this number right here is kind of like the 0 that we had in our previous problem. You're going to hold off on using that 15.9 until you've made your interval and see, well, does 15.9 actually fall on this interval? Now, this is not perfect here because just looking at Pennsylvania schools is not necessarily a random sample of nationwide schools. Okay? But they're randomly selected across Pennsylvania. So just go with it. Okay? You have your X bar, you have your standard deviation sigma, you have the sample size, 50 Pennsylvania schools, you can find that confidence interval. Okay? Number 2, random sample of 200 Upper St. Clair students asked how much money they spent on entertainment in the past week. X bar is $28, standard deviation of $18, 95% confidence interval of what they truly spent. The third and final question is a little bit different because what we're usually doing is collecting our own data. And you're not provided with, here's the mean, here's the standard deviation, here's the sample size. No, you have raw data that you need to calculate those things and make your own confidence interval. So we have a small town that wants to raise money by installing parking meters. So they look at a neighboring community and their parking meters. They took a sample of 20 of them. And here is the daily revenue. What you're going to do is make a confidence interval for the true average daily revenue for the population of parking meters in this town. My suggestion, use the list on the calculator or spreadsheet or GeoGebra. Do the 1-bar stats. Get the sample mean, get the standard deviation, and then do your calculation. So let's take a few minutes, like 10 minutes or so, do that, and we'll talk about these. Any questions before you get started? All right, go ahead. I want everybody doing this.